Welcome to this video on writing a scientific equation. It's part of the model building process. Now remember, a model is an equation or something else that's mathematical perhaps that can make a prediction. So in this case, what I'm going to be looking at is a ring stand here that has a spring attached, and I'm adding mass to the spring and seeing if there's a relationship between the amount of mass added and how far the spring stretches. So I'm gone up and adding 10-gram increments of mass, and as I add increments of mass, I want to see how does the stretch change. So I collected my data and I graphed it, and I graphed it using Excel. And the reason I did that was because I wanted to get a trend line or a line of best fit that is a little bit more accurate to the actual data set trend rather than one that I could do by hand. But I'm going to be doing everything else by hand in this video. So over here at the top right, you can see I have the steps that I'm going to use throughout this video, and at the end you can take a screenshot and use that as a little cheat sheet, if you will, for when you're doing some of these by yourself. Now, the very first thing that we want to look at here is that when we graph our data, we are trying to come up with an equation. So the shape that the data creates in the trend line is going to tell us what generic equation to use. So let's go ahead and do that. Now I've already graphed the data, but you can use, maybe Excel or Logger Pro or something else to graph it. Now we're going to label the axes with titles and units. Now you can do step 2 ahead of step 1. I'm going to do it this way just for the example here in the video. So my independent variable, or my horizontal axis, is going to be the mass, and that is measured in grams. And my vertical axis is going to be the stretch. You might even call this stretch distance, but stretch is fine, and that is in centimeters. Now when I title my graph, the convention is to do the vertical versus the horizontal, or y versus x. So in this case, that's going to be stretch versus mass. Okay, so I've got meaning now added to the graph. It's not just a random line. And now I'm going to write the general or the parent function, and then I'm going to make some changes to it. Well, I see that the trend line is linear, and a linear shape indicates the equation y equals mx plus b. So I know that I'm going to have to add in a slope value here and a y-intercept value here, and I'm going to have to change y and x to fit the actual experiment, because I'm making a scientific equation here, not just a generic math equation. Alright, so it's time to calculate the slope. And because this is a scientific equation, the slope needs to have units attached to it. So we'll take a look at that at the same time. So let's go ahead and calculate the slope. Well, to calculate the slope, we need 2 points, and we need 2 points that fall on the trend line. This is super important, that we don't pick data points. The data points are a thing of the past now. We already used them to make the trend. Now we're focusing on the trend. So what I'm going to do is pick 2 points. I'll go ahead and pick this point right here, and maybe this point right here. Okay. Those 2 purple points, I'll go ahead and circle them. Those are not data points, right? They fall on the trend line. So this point looks like it's about 40, 15, and this one looks like it's 20, it's just below 10, so maybe you'll put 9. So over here I'm going to calculate the change in the vertical variable over the change in the horizontal variable. So it's just a case of finding the difference for how much it changed. Alright, so let's do that. So we have 15 minus 9 over 40 minus 20. That's going to give me 6 over 20. And 6 over 20 is the same thing as 3 over 10, which is the same thing as 0.3. So I'm going to leave mine in this decimal form, because to me that's a little bit easier to actually measure. Now, if we were in a math class, we could stop right there and put it in, but because this is a scientific graph, we need to actually include the units of this. So we do just exactly what we did here. We just put the units on the top and the bottom so that they relate. So the units of the top were centimeters, or the units of y, and the units of the x variable, the horizontal variable, was grams. Now the important thing with the slope is when you've written out your final slope, we have 0.3 centimeters per gram. We want to make sure that this denominator is actually a singular word, so not plural. So instead of saying grams, we want to actually cross out the s here and say that this is 0.3 centimeters per gram, okay, singular. Now that's important, and I bring this up because when somebody asks you, well, what's the physical meaning of the slope in this case? If you just say, well, it's 0.3 centimeters per grams, that doesn't really make a lot of sense physically. But if I say 0.3 centimeters per gram with no s, then what I'm saying is that this spring will stretch 0.3 centimeters for every 1 gram that's added to the spring. So it gives it meaning that's a little bit closer to how we would speak in, actually describing this. So I'm going to go ahead and substitute this in now into my equation. So I have y equals 0.3, and I need to put my units, centimeters per gram. Okay, now this does not mean that I'm multiplying centimeters over grams. This is the unit itself, right? Now I have to put my x, and now I'm going to put my y-intercept, which we're symbolizing with b. So I calculated the slope in the units. Now I need to replace the variables. So when I say replace the variables, I mean this graph does not have y on it. It has stretch and it has mass. So I'm going to go ahead and replace those here in this little equation. So let's go ahead and replace y with stretch. I'm going to go ahead and put, again, 0.3 centimeters per gram. X is, of course, mass. And then I need to calculate b still. And that's going to be my next step. So I just replaced my variables. Now I'm going to calculate the y-intercept and the y-intercept units. To calculate the y-intercept, what needs to happen is I need to pick a point on this trend line that I can substitute into my equation and then isolate or solve for b. So I'm just going to pick one of the points that I already have here. Let's go ahead and pick 40 and 15. So I'm going to go ahead and say that I'll write a short version of this. So I'm going to use S for stretch equals 0.3 centimeters per gram. I'm just going to use M for mass plus B. So I'm just using a short version here. Okay, so I'm going to pick the point 40, 15, which basically 40 is a mass value and 15 is a stretch value. So when I'm going to plug them into this equation over here. Okay, so my stretch is 15 equals 0.3 centimeters per gram. I'm just going to leave the units out for right now. The mass is 40, and then I'm going to put plus B. So B is what I'm actually solving for. Okay, so I have 15 equals 0.3 times 40 is 12 plus B. Now to get B by itself, I'm going to subtract 12 from both sides. And 15 minus 12 will leave me with 3. So I see my y-intercept is 3. Now keep in mind, this again is a scientific equation, so I have to add units. So I'm going to go ahead and look at the graph to figure out what the units are. Well, B is really just a special version of Y, so whatever the units of Y are automatically the units of B, and that is the centimeter. So I'm going to put here, this is actually 3 centimeters as this unit. Okay. Now it's time to write the final equation in here, and I'll go ahead and write this down here in the bottom. Let me scroll this back so you can take a little screenshot if you would like to. Okay, so it's time to write the final equation here, and I'm going to put stretch, you could use just S, equals 0.3 centimeters per gram times mass plus 3 centimeters. So keep in mind that this is the slope with the units and this is the y-intercept. So what this is saying is that you can predict the stretch by saying that every time 1 gram was added, 0.3 centimeters stretch increased. I can take whatever mass I want to put on the spring and multiply it by that constant, add 3 centimeters, and I'll have automatically the stretch distance. So that's the general process for writing out the scientific equation from the graph.